Hello, everyone. My name is Pablo Ghiglino. I am the founder of Klepsydra Technologies, a company based in Switzerland that is focused mainly on high-performance software development for onboard systems. I wanted to thank the opportunity to present in this conference. I'm very excited about this, and I hope you find what we present interesting. It's very connected to what was just presented, but from the software perspective. So yes, we develop software that is high performance oriented to onboard systems. By high performance, we mean do more with less. We try to achieve more data processing, more artificial intelligence with less energy consumption. And how do we do this? Our technology is based on something called log-free programming. Log-free programming is an approach to parallelization strongly used in the financial industry, where I have been working many years. I am an aerospace engineer by studies, but my profession always drove me towards investment banking development. But now I'm back to aerospace. Thanks a lot. Yes, why we apply this? Because there is a growing need to perform more data processing on board computers. And the speed at which data grows on board is faster than the speed at which computing power grows. So there are some issues being faced by this, no? In terms of amount of data that can be downloaded from Earth observation applications, or latency issues in the case of precision landing systems, etc. So going back to the log-free programming. Log-free programming comes from a more lower level concept called compare and swap, which is a specific assembly instruction related to how the memory is managed in different processors. This was created by IBM back in the 70s, but it wasn't really until the early 90s when it was introduced in the higher level languages like C++ and Java that it became popular. And it boomed in the early 2000s when the banks started using this technology. So log-free, going back to the concept of log-free, it's usually depicted as like the Los Angeles airport, a very busy airport with planes having to do loops until they manage to find a free slot and manage to land in the gateway. Log-free works exactly the same way. You try to update the memory to leave it in a consistent state. We try, fail, okay, you try again, etc., until you manage to leave the memory in a consistent state. So it's like a busy wait. What is in programming is used to be called busy wait. And this approach is, although it's busy wait, is much more efficient than traditional log techniques. So when you have to do a log between two threads, you have to do a mutex, you have to do some kind of context switch between the different threads. And this is quite a heavy process. Log-free, on the other hand, is more granular, although a busy wait, and the fact that it's granular makes things more lightweight. In fact, one of the things that was developed in these investment banking trading systems was the fact that processors can scale linearly. So if the amount of data grows double, you use double amount of CPU. So this is a very important, if the algorithm written with log-free programming is sophisticated and efficient enough. It's not just by using an atomic operation you will get that. No, you need some kind of advanced algorithms to achieve this level of performance. On the other hand, the bigger complexity of this is the conversion of programming with log-free techniques. Doing a mutex is very simple. Pretty much every programmer can do it, but log-free requires a little bit more work. So we have done this for the normal developer user. So we have developed what we call the SDK, which is a log-free programming framework that enables parallelization. Out of which we have developed three different products. One is for the artificial intelligence inference engine that we have, which is the focus of this presentation. We have another product for ROS2 acceleration. There are some elements in this conference about ROS2, but we're not presenting, but there is a video. We have a video presentation in this conference about this if you're interested. And there is also a GPU work that is a little bit out of the scope of this presentation. So the SDK, like I said, is a multi-threading framework. It's a parallelization framework in essence, with some plugins for different things. But the key thing is the API, or the algorithms we have implemented. We have two algorithms. One is a so-called data multiplexer or sensor multiplexer. We have one source of data, and you have multiple consumers. A consumer in a different thread of the same data. This is a typical case of an image, a camera, where you want to compress the image, you want to use it for AI on board, etc. With this parallelization framework, you have multiple threads using the same data without copies. The data remains live while the system needs it, etc. It's quite efficient. And on the other hand, we have the other API, which is the event loop, which is the focus of this presentation, where you have multiple producers of data and one consumer, which is basically streamlining all the data from the different producers into the single consumer. So this is the inspiration of the trading system, because in trading you have multiple sources of data, customer orders, pricing systems, etc., and you want to streamline all this as efficient as possible. So this is the origin of this technology. Important thing is that these two APIs are very energy efficient because they are built on lock-free techniques. They are very high throughput, and the latency is quite low in terms of data processing. Obviously, there is a limitation, physical limitations of the processor at hand, but they are quite efficient. So what has this anything to do with artificial intelligence, no? Which is the goal of this presentation? So leaving for a moment the lock-free programming, there are two approaches to execute algorithms in general. One is the traditional parallelization that most of software engineers are familiar with, which consists on splitting. For example, if you have a matrix multiplication, you split into smaller identical pieces, and each thread start processing their own piece, no? Until you collect it all at the end. The typical example is OpenMP, which is a framework especially built for that. However, there is another approach called pipelining. It's quite old, but it's becoming, it's kind of been resuscitated lately, because it's quite efficient in terms of energy consumption and also quite high throughput as well. And pipelining means it's building, it's exactly what the image tried to show. It's like an assembly line, where each part of the algorithm is split into a different thread or a different resource, and you start assembling your data. No? So if it's an image processing, each phase of the image processing will be split into different threads. So we started doing some testing of this when we decided to use our API for algorithm optimization. And the first thing we did is compare the two things, compare parallelization using OpenMP and pipelining using the Klepsydra event loop. In this case, it's a simple sequence of matrix multiplications. In one case, we just split it as a pipeline, and the other case was OpenMP parallelization. So we tested with different parameters, with floats, integers, different number of steps, different dimension, etc. But the overall results are shown here. As you can see, pipelining is exactly what I mentioned. The consumption of CPU is very low. So this is quite a good advantage of the pipelining. And the throughput is good. And the more complex the algorithm, the better the throughput you will get with pipelining. There is a drawback, which is the latency, as you can see here, which is much higher, but I will come back to that because this is something we have been working quite exhaustively here at Klepsydra. So how do we apply this technology to artificial intelligence? This is a simplified version, so in case you have a simple deep neural network, which is a sequential deep neural network where all the layers are one after the other. This is not the real case because many networks have graphs. But if you take this example, you take the X number of layers associated to the first event loop, and this is the first element of the pipeline, and so on. So this is one way of performing a pipelining. And of course, with this, we will get a substantial power reduction and substantial throughput increase. However, there is a latency issue I just mentioned. So for that, we introduce a second dimension of threading in our system, which is using the traditional parallelization. So in reality, we're combining the two things. We're combining a pipelining approach, where we split the AI in different parts of the assembly line, and at the same time, for those layers that are particularly heavy, we use the parallelization. So this is why we call it a two-dimensional threading model. And what is the advantage of this? The advantage is very much related to the different needs of the space onboard AI applications. So if we do purely pipelining, as you can see on the left, what we get here is very low CPU consumption. So in case of applications that want to run AI, but they don't care so much about latency, and what important is the lowest possible consumption, you can just do a pipelining, and the consumption will be very low. Will be maybe 50% less than with other techniques like another inference engines like TensorFlow Lite. On the other hand, if you want to have a very low latency, you can use a minimal pipelining and then parallelize as much as possible the different parts. And with this, you will get a substantially low latency too, also substantially lower than TensorFlow Lite. So this is the main goal of our inference engine, is to offer different configurations for different needs. So in the case of low latencies, the type of typical case of planetary landing or vision-based navigation, where the latency is critical. High throughput is more interested in the case of Earth observation, where maybe the difference in a few milliseconds is not so important, but processing as many images as possible it is. So at the end, you get a range, right? You get a range of elasticity, elastic range, how you can configure the inference engine. However, this process can be quite complex. So one of the things we have started working on, and is one of the new areas of research in our company, is what we call the Klepsydra streaming optimizer. I used to call it a Klepsydra layer streaming distributor, LSD, but the name didn't really sound very adequate, so we renamed it to Klepsydra SO. With this, we use genetic algorithms. So we run a few dry runs of the inference engine, and then genetic algorithms will take this and try to find the best combination of these two-dimensional threading. So assigning different layers and try to even out. In reality, the goal of this is to try to even out the load in the different processors. Some of the research shows that the more balanced the different cores in a processor are, the better the energy consumption is. So this is one of our goals of this genetic algorithm. Why genetic? And one can just say a simple rule to calculate mathematically what are the latencies of the different layers is because of the graph thing that I mentioned. In a sequential neural network, it is easy. It's very easy to say, okay, these layers go to this core and these layers go to this other core. But in the case of a graph, where you don't know exactly which part of the two parallel branches is require more effort, you prefer to do this with a genetic algorithm. The results are substantially better. And this is some of the examples. No? In this case, it was the genetic algorithm concluded that 3 cores should be dedicated to the pipeline. They are more or less balanced. The extra core is used for parallelization, and with this you get some good results. This is a simple example of what the AI algorithm, genetic algorithm is doing. This is done just once, by the way. You just do it once on your AI model on the target computer, and then you get these results. So this is the API of Klepsydra. It's in C++. I know there was some animosity towards C++ today, but I am a hardcore old school developer, so everything is in C++. But the API is quite simple. It's like any other inference engine. The main difference is that it's asynchronous because we use these log-free techniques and everything is multi-threaded. We don't know when the engine will be finished, so we give control back immediately to the developer after invoking the predict, and then a callback will be triggered later on with the results. This is the main difference with other inference engines. Now, finally, I'll talk about how this started. This started with a project called Katesu, run by ESA. ESA commissioned Klepsydra to run our inference engine in different space qualified computers, especially ARM processors. And we tested in two ARM-based processors, one by NXP and Teledyne called the LS1046, which is a 4-core ARM computer. We run it with Yocto Linux and Docker inside. So we use ESA also wanted to see how Dockerization may work in this kind of processor. So we run Klepsydra on a Docker inside the LS1046. The results were very good because we have two variations of our mathematical backend. One is full backend, full support, so also for floating point calculations, another for only quantize. And in this case, we could install both of them. And also we tested in a smaller ARM processor, 32 bits, no? Which is the Z board, a dual core processor, also with a Peta Linux, embedded Linux with the Docker installation inside. In this case, we could only install our quantize engine software. But the performance were very good. Sorry, here it is. This is a model developed by ESA in a project called OVP Mark. It's a CME. It's called coronal mass ejection detection. So it's basically to detect ejections of solar mass that may affect the weather conditions for the satellite and that may affect the way to when to do downlink connections because this have an effect on the downlink. And as you can see, for different these are not one configuration. There are three different configurations to check the main three elements that we check, which are the CPU. In this case, if we optimize for CPU, we can get less than 50% of the consumption that TensorFlow Lite needs. Also using the Neon instruction. As you may know, the TensorFlow Lite has an acceleration for ARM using the Neon instruction set. Also for throughput, we also achieve a 3 times more throughput and 1/3 of the latency. This is very good results. We also run a quantized version. Quantized is always a little bit unpredictable. What happened with quantized? In this case, the CPU was not so much reduced, but the latency is. So in some cases, it's the other way around. So it depends on the way that things are quantized. And also in the Z board, we run it on the Z board with very good performance results as well, as you can see. So we managed to run it there, which is a very small computer. This for me was a very good, very important landmark in our company because this is a very small processor and we managed to run AI very efficiently there. And finally, we run another model developed by the Barcelona Supercomputer Center. We collaborate a lot with Leonidas, who is going to present tomorrow, and this model we also run. There is also part of this OVP Mark system of ESA. This is an example of this. This particular model does cloud detection. You can see in the left side the full image, on the right hand only the cloud coverage of the image. And we managed to run it very efficiently, as you can see. So up to, well, TensorFlow needs almost 4 seconds or a little bit more than 4 seconds. We did it in just a little bit over 1 second. So this is, in a nutshell, what Klepsydra has been doing last year. And this year, we have a plan to do a number of other things. One thing was the extension to GPUs. Like I mentioned, it's not very relevant, but one of the things we're doing there is to increase occupancy. One of the issues we run in AI on GPUs is that you don't use all the GPU resources. With our software, we try to parallelize even more and get a higher GPU occupancy and therefore increasing the throughput. Also, we are working to expand our inference engine to FPGAs as well. Another important thing is support to FreeRTOS and Artems. I think there are some people from Artems here, so we are going to start working on that together with ESA as well. And also the support to a number of other processors. The main goal of this year is to support the GR740 and the GR765, both in Leon 5 and also in RISC-V versions. And finally, we're going to expand as well to some European coprocessor. I don't think this is well known here in the US, but it's called HPDP. It's a coprocessor developed by a company closely connected to Airbus. Okay, I think that's it from me. Thank you very much. Let me know if you have any questions.